which is affected by the competition between Rashba and Dresselhaus spin-orbit interaction. And this work was done together with my colleague in Tohoku University, and some of the theoretical part was supported by the Richter's group in Tohoku University. And probably the most of the people here knows about the spin-orbit interaction, which gives rise to the effective magnetic fields on moving electron. Especially the Rashba spin-orbit interaction is quite important because the strength can be controlled by the gate electric field. So based on this gates controlled feature, we have proposed the spin interference device, something like this, and we could successfully demonstrate that spin precession angle can be controlled by the gate electric field, something like this. So this is advantage of using spin-orbit interaction. But on the contrary, the spin-orbit effective magnetic field is momentum dependent, something like this. So after the scattering event, this effective field shown by this arrow is changed. So therefore, after the several scattering event, the spin orientation is completely randomized. So this is so-called the spin relaxation. And the easiest way to monitor this kind of spin relaxation is, for example, in the transport measurement, is to measure this weak antilocalization. This quantum correction to the conductance gives rise to the negative interference effect. This negative interference effect is destroyed by the magnetic field. So this makes this negative magnetic conductance. So when you have a strong spin-orbit effect, we have such a larger negative magnetic conductance. And if you have the weak spin relaxation, this conductance is getting weaker and weaker. So therefore then, by measuring this kind of magnetic conductance, we can monitor the strength of the spin relaxation. So this is the point of my talk today. So the question is how to suppress this the spin relaxation. There are several ways, and so one of the ways is by applying the Zeeman effect, and we can suppress the the spin relaxation. And another way is by using this the wire structure, because of the geometrical confinement can also suppress the spin-orbit interaction. So we will discuss about these kind of two effects in my talk today. And so the content of my talk today is much focusing on the suppression of the spin relaxation, which is modified by the weak antilocalization. And the first part of my talk is about the competition between the spin-orbit interaction and the Zeeman effect. First, I will discuss about in two-dimensional electron case. And also these two effects are quite important for the spin dynamics in solids. And also this competition gives rise to a quite interesting property in the dephasing effect I will show you later. Then I will discuss about the competition between Rashba and Dresselhaus spin-orbit interaction. So recently we have proposed a novel way to detect the ratio between the Rashba and the Dresselhaus spin-orbit interaction, and I will show the measurement principle and also show our very preliminary experimental result to detect this ratio. Then I will discuss the anisotropic spin transport in wire structures. So we have observed very strong anisotropy in spin transport in wire structures. And also we have observed large enhancement of the spin relaxation time and length. So this suggests the so-called persistent spin helix condition. So I will show this experimental data. Okay, let me start with the competition between the Zeeman effect and the spin-orbit effect. And the system we are using is indium gallium arsenide based two-dimensional electron gas, which has a strong spin-orbit interaction. I mean, the stronger than the gallium arsenide case and silicon case because of the narrower gap, the material. And the experimental setup is something like this. The Zeeman effect was introduced by applying this in-plane magnetic field. Actually, this applied in-plane magnetic field is completely in parallel to the two-dimensional electron gas. So that doesn't disturb any orbital motion of the electron in the two-dimensional electron gas. And we have also applied quite small perpendicular magnetic field to probe the strength of the spin-orbit interaction and spin relaxation. And this is the result. So as you can see, without in-plane magnetic field shown this the red curve, we have observed this conductance peak near p equal to 0. And by increasing this in-plane magnetic field, you can see this conductance peak is getting weaker and weaker, and spin relaxation is suppressed by the external in-plane magnetic fields. And when the in-plane magnetic field is something like 2.5, so this conductance peak is completely suppressed. So that means the strength of the effective field due to the spin orbit is something like 1 or 2 teslas in this present sample. And this is the blown up of this part, and this red curves the theoretical fitting to the experimental data, and from this fitting we can extract the two important transport parameters, namely spin relaxation time and the dephasing time as a function of the in-plane magnetic field. So yeah, this is the spin relaxation time as a function of the in-plane magnetic fields. And as we expected, this spin relaxation time is going up by increasing the in-plane magnetic fields. So this is because this momentum-dependent spin-orbit field, shown by this the green arrow, is partially aligned to the external in-plane magnetic fields. So this makes the spin relaxation longer. So this is very qualitative explanation. But on the other hand, if you plot this dephasing rate as a function of the in-plane magnetic fields, so this is going down by increasing the in-plane magnetic fields. So this is so-called the spin-induced the dephasing rate. I will discuss more detail in the next view graph. And more interestingly, if I extract some additional dephasing rate, so this is the total dephasing rate with in-plane magnetic fields, and this is the dephasing rate, so-called inelastic scattering rate, without in-plane magnetic fields. So if I plot this quantity as a function of the ratio between Zeeman energy and the spin-orbit interaction energy, and all experimental data graphs into one single curve, something like this. So it's very, looks like universal. And the interesting point is it does not depend on any detail of the two-dimensional electron gas. Namely, it does not depend on the carrier concentration, and it does not depend on the electron mobility of the two-dimensional electron gas. So actually, this universal behavior was explained by this theory. So this theory is a little bit complicated. So I would like to explain more intuitive way. For example, if you have only the spin-orbit interaction, for example, in the Rashba spin-orbit interaction, basically the spin-orbit interaction does not break any time reversal symmetry. So it does not affect on the dephasing time. But if the spin-orbit interaction is combined with the Zeeman effect, so this is the spin subspace due to the Zeeman effect. The point is, this Fame wave number between spin up and down is different when you apply external magnetic field. And for example, if you have a scattering and the electron state is scattered from here to there, the electron spin up down is mixed. But in this, the Zeeman field, the wave number between spin up and down is different. So if you look at this time reversal symmetric interference loop, the acquired phase of the clockwise direction and the counterclockwise direction is not anymore identical. So by increasing this Zeeman effect, the phase difference between these two acquired phase getting larger and larger. So this is the origin of the spin-induced, the dephasing rate. And if you have the very strong the Zeeman effect, so these two spin subband is completely separated, then the interference can occur the separate way. So this makes the saturation of the dephasing rate. So this is a very qualitative explanation of this of the previous experimental result. And let me go back to the spin relaxation. Another way to suppress the spin relaxation is using this one-dimensional wire structure. So if it is pure one-dimensional wire, even in the presence of the spin-orbit interaction, or the diagonal parallel type of the spin relaxation is completely suppressed because the acquired phase between this and this is exactly the same. Because if the effective magnetic field is uniaxial, so the spin rotational operator can commute something like this. So the acquired phase here and here and here is just cancelled out. So this gives rise to the same the phase difference here. But quite recently, theory predicts that even the wire is not pure one-dimensional. If the wire width is smaller than the spin relaxation length, something like this, still we can expect the spin relaxation. And according to the theory, when this condition is satisfied, the wire can be treated as a quasi one-dimensional wire. So the first experimental demonstration was done by Thomas Schaefers in Jülich Institute. So they have made the several different widths of the wire structure, which is also made from made of individual arsenides to the major electron gas. So what they have observed was something like this. When the width is quite wide, they have the conductance peak due to the spin relaxation. But by decreasing the width, you can see the crossover from weak anti-localization to weak localization was observed in this wire structure. And another experimental was done by the David Ocean group in Santa Barbara. Actually, they have directly observed or measured the spin relaxation time by the optical bone control experiment. And spin relaxation time was also increased by decreasing the wire width. So this is because of the such a random the motion of the electron is a little bit confined by some geometrical confinement can align the effective field due to the spin-orbit interaction. So this is very, very intuitive picture of the enhancement of the spin relaxation time. But more essentially, there are quite excellent method to enhance the spin relaxation. This is so-called persistent spin helix condition. So when the Rashba spin-orbit interaction alpha is equal to beta, beta is the strength of the Dresselhaus spin-orbit interaction. And in this case, the effective magnetic field due to the spin-orbit interactions are uniaxial, something like this. So in this condition, as I mentioned, the spin can be very conserved, very preserved, the quantity. The another thing is even after the scattering event, for example, something like this, if one of the spin is injected from the ferromagnetic electrodes, and after the several scattering event, and actually these three different trajectories provides the same precession angle, something like this, along 110 orientation. Actually, this was first proposed by the Daniel, he's sitting over there. And so therefore, it's very important to evaluate this quantity. And therefore, we have proposed the novel way to detect this alpha and the beta ratio. Okay, let's assume this is a quasi one-dimensional the wire structure. And if it is something like a wire structure, the Rashba effective fields is something like this. This is always perpendicular to the momentum orientation, something like this. And the Dresselhaus spin-orbit interaction is like this. This has the two-fold symmetry, but when you reverse the momentum direction, the effective field direction is also reversed. So the total effective field is still uniaxial, something like this. So in this case, the spin relaxation is suppressed in this wire case. So the point is we try to apply in-plane magnetic field. So this in-plane magnetic field is still in parallel to this effective field due to the spin-orbit interactions. Still, this uniaxial magnetic field condition is satisfied. Then still the spin relaxation is suppressed in this case. However, this effective external magnetic field is not aligned to the spin-orbit induced field. So the total magnetic field is not anymore uniaxial. Then we have the enhancement of the spin relaxation. So we have the conductance dip at the p equal to 0. So actually this angle, so this in-plane, the parallel angle can be obtained after the very, very simple mathematical calculation given something like this. So this alpha and beta is a spin-orbit interaction. And this, the phi is angle from the 1, 0, 0 orientation. So to check this, the theoretical expression, so we have made the numerical analysis. Actually, this numerical calculation was done by the students from the Regensburg University. So to make it a simple situation, this wire is put around the y direction, 0, 1, 0 direction. And for example, if the alpha equals 0 and the beta is finite, so in this case, the effective field is along the y-axis. So in this case, the conductance minima appears around the pi over 2, which is expected in the expression. And for example, in the case of alpha equal to beta, so in this case, the effective field direction is 135 degrees. Actually, this minima appears around this angle. And so this equation is quite useful to detect this alpha and beta. So all numerical results is summarized of these black dots, and which is compared with this theoretical expression, and actually it is to agree quite well. And more importantly, this is quite robust against the change in this the parameter. For example, if I change the width of the wire structure or change the two parameters, still the minimum conductance minimum appeared at the expected position. So this is quite important to the real experiment. So to check this our theoretical or proposal, so we have made this wire structure. And wire is also made of this indium gallium arsenide, the base two-dimensional electron gas. And this wire consists 120 wires to suppress the universal conductance fluctuation. And also the wires are covered with a gate to control the Rashba spin-orbit interaction. And another, probably the most important thing is this wire direction is 1, 0, 0 orientation. Because, this is because to suppress the cubic Dresselhaus term effect, which has the like this four-fold symmetry it's very strong around the 1-1-0 orientation and 1-1-1 orientation. So in this direction, the cubic Dresselhaus term can be negligible. Then we had the measurement by applying the different angle of the in-plane magnetic fields. So this is one of the examples. When we apply in-plane magnetic fields along the 1-0-0 orientation, so we have also seen this the crossover from weak anti-localization to the weak localization. But this crossover happened around the 0.9 or 1 Teslas. But on the other hand, if we apply the in-plane magnetic fields around the in parallel to the Rashba spin-orbit interaction, this is 90 degrees. So in this case, the crossover happens around the 0.6 Teslas or something like this. This is much smaller than the other one. So it already shows the strong anisotropy in the spin transport. So this experimental suggests that the effective magnetic field due to the spin orbit is very close to the 90 degree. So that means the strength of the Rashba spin orbit interaction, the spin effective field induced by the Rashba spin orbit interaction is stronger than that of Dresselhaus spin orbit interaction. So to go forward, we have made a more detailed experiment, but before doing this angle dependence, we have checked this rotation of the sample without applying the in-plane magnetic field to get rid of some artifact or something like this. And we have observed this quite isotropic. This is the angle, and the magnetic conductance is quite isotropic. So that means this sample rotation does not make any artifact. Then we apply the in-plane magnetic fields and measure the angle dependence. So as you can see, we have observed such quite strong anisotropy. For example, when we apply in-plane magnetic field, something like 75 degree, so the weak anti-localization is minimized. But if you apply 165 degree, the weak anti-localization is maximized. And actually, from this experiment already suggests that the spin, the ratio between alpha and beta is something like almost 4 or something like this from this angle. And this experimental data was compared to the theory recently developed by Ketman, which can be applied to the wire structure. And this crosses the calculation, and from this the comparison we can get this spin relaxation length and the dephasing length. And this is the spin relaxation length as a function of the in-plane magnetic field angle. And in this case, as I mentioned, the spin relaxation length has maximized at the 75 degree. But on the contrary, if you look at this dephasing length as a function of the angle, so this maximum position is 90 degrees shifted, something like 165 degrees or something like this. So why this happened? So as I mentioned that this is actually two-dimensional case. So the one-dimensional case is a little bit different, but we can explain by this experimental result. So when the Zeeman energy is much smaller than the spin orbit energy, then this L-phi and spin relaxation time is inversely proportional relation. So in this case, the dephasing length should be maximized at the spin orbit scattering time is minimized. But on the contrary, if the Zeeman field is much stronger than the spin orbit energy, so in this case we have observed this saturation. So in this case, the dephasing time is proportional to the spin relaxation time. So this should be also observed in our experiment. Actually, it does. For example, when the spin orbit interaction is quite strong. And we have weak anti-localization case. So in this case, okay, this is dephasing length. We have the maximum at 165 degrees, but by applying the positive gate voltage, the spin-orbit interaction is weaker, so we have the crossover to the weak localization. So in this case, the peak position is almost 90 degrees shifting. So the tau s and the tau phi are getting the same relation. So more detailed experiments are done, and by using this, the angle when the spin relaxation length is maximized and the dephasing length is maximized, we can determine this alignment angle. And this is the summary of the results. And the Rashba, the spin-orbit interaction was obtained from the two-dimensional ordinary Hall structure. And also the angle of the alignment angle was obtained from the previous experimental results, and all experimental data are brought somewhere here. And the most suitable or good the fitting can be obtained if we assume this beta parameter here, something like 1 times 10 to the minus 12 electron volt meter. And actually, this is quite agree with the textbook from the Laura Winkler. And this the linear Dresselhaus term is given by this cubic Dresselhaus term coefficient, and also depend on the quantum well-width. And this gives something like 0.8 times 10 to the 12, or something like this. So this suggests that this kind of measurement is quite effective to obtain the ratio between Rashba and the Dresselhaus spin-orbit interaction. But we are still wondering, because this Dresselhaus coefficient is quite scattered. Sorry, this is a little bit small, but in theory, the highest the Dresselhaus spin-orbit parameter is something like this, but the minimum is something like this, almost 1/3. Also in the experiments, the experimental data is quite scattered. Actually, this is gallium arsenide case. And also this theory insists that at least in this gallium arsenide quantum dot, this is most commonly used value, but it was something like 9. So we should careful. And actually, our experimental data is still have a large error bar, so we still try to make it more accurate data. And the Dresselhaus cubic term was it's obtained from this K.D perturbation theory, and actually this is material constant parameter. If the material parameter is correct, so then we should plug into this one. And the interesting point is the gallium arsenide and the indium arsenide, which has a quite different energy gap, but just coincidentally, these two material give rise to the very similar parameter. But on the other hand, the indium gallium arsenide is not in between. This is a little bit larger than this value, so we are a little bit careful to decide this Dresselhaus parameter. I think it's still challenging to determine this value. And quite recently, actually, this was done last year by the UC Berkeley and Santa Barbara, and also the collaboration with the UC Santa Barbara group they claim that they have observed so-called persistent spin helix condition. Actually, they have measured the large enhancement of the spin relaxation time by changing the Rashba spin-orbit interaction by using 5 different quantum well structures to control the Rashba spin-orbit interaction. And actually, yeah, the obtained gamma parameter is 5, still very small, so we should try to figure out what's going on. This is actually gallium arsenide system. So we also try to realize this, the persistent spin helix condition, but quite different way, by using this wire structure. And this wire is also covered with gate to control the Rashba spin-orbit interaction. When the wire width is quite small, the weak anti-localization is completely suppressed, and spin relaxation is suppressed. We can only see this weak localization. But with relatively wider wire, we have observed this crossover from weak anti-localization to weak localization. And actually, these experimental data was compared with the Kettmann theory, and we can extract the spin relaxation length as a function of the gate voltage. So as you can see, by decreasing the wire width, we have the enhancement of the spin relaxation length. But by decreasing or increasing the carrier density, we have a large enhancement of the spin relaxation length. So this can be explained by the fact that this Rashba parameter is approaching the beta parameter somewhere here. So actually, this is a very good indication of the persistent spin helix condition, that I'm not completely satisfied with this result, because if it is a persistent spin helix condition, it should show a strong anisotropy in spin relaxation. So let me explain briefly. So when you have only Rashba spin-orbit interaction, the effective field direction is something like this, which is always perpendicular to the momentum orientation. But the strength is quite uniform, something like this. On the other hand, if you have only Dresselhaus, this is two-fold symmetry, but the strength, again, this is also very uniform. But if you have both, okay, alpha and beta is equal, like this, the direction of the effective fields is uniaxial, but the strength is quite anisotropic. For example, 1, 1, 0 direction, this is maximum. But 1, 1, 0 direction, which is almost 0. So we should observe this kind of anisotropy to say the persistent spin helix condition. So to confirm, we have made this the wire structure, which has the 3 different crystal orientation. We made this the sample at the same time, and we put the same gauge electrodes, and we have measured this sample at the same time. And actually, this is the wire width dependence of the conductance. And okay, it already shows some anisotropy, but this anisotropy is much enhanced by decreasing this wire width and by comparing with the theory. So when the wire width is relatively wide, this is more or less anisotropic, but by decreasing, like this, it shows such a strong anisotropic spin relaxation, which is something like this. When the wire width is smaller than 1 micrometer, this anisotropy is much enhanced. The large anisotropy was observed in this wire structure. And actually, this is the carrier density dependence, and by increasing the carrier density, and also the anisotropy is getting larger by increasing the carrier concentration. And actually, this anisotropy is very qualitatively explained by the very simple theory. And I should also mention that if the cubic Dresselhaus is still very strong, it should show this 4-fold symmetry, but our experimental data is quite different from this. So that means the cubic effect in this wire structure is very weak. And this is more detailed data of the magnetic conductance as a function of